Okay, let's dive right into this. Today, we're taking a fascinating textbook engineering concept and really bringing it to life. We're looking at how modern, heavy-duty manufacturing actually gets done on the factory floor. So we're unpacking Chapter 25 from our source material, Machining Centers and Machine Tool Structures. If you've ever held a complex metal part and wondered how on earth it was produced with such absolute precision, well, you're in the exact right place. Let me start by posing a question that honestly plagued engineers for decades. How do you build complex parts without moving them? You see, traditionally, manufacturing was kind of a logistical nightmare. Just imagine a raw block of metal that needs to be milled, drilled, bored, and threaded. In the old days, that meant physically moving that heavy, partially finished workpiece to a dozen different dedicated machines. You'd set it up, machine a hole, unclamp it, move it across the factory floor, set it up again on a different machine, and just cross your fingers that you didn't lose any precision along the way. It was time-consuming, expensive, and frankly, highly prone to error. And this brilliantly illustrates exactly what we're talking about. Just consider a forged motorcycle wheel. Now, this isn't just some simple block of metal, right? It requires complex, near-net shape finishes. Even if it starts out as a forging or a precision casting, it still needs exact finishing operations for things like the axle holes, the flat surfaces for the brake rotors, threaded holes, and those incredibly smooth, polished curves. If you had to unclamp and move this heavy wheel to a different machine for every single cut, bore, and thread, it would cost an absolute fortune. So how does modern manufacturing solve this giant puzzle? Well, here's our roadmap for this explainer. First, we'll look at the need for flexibility. Second, enter the machining center. Third, the anatomy of the machine. Fourth, the types of machining centers out there. And finally, capabilities and economics. All right, Section 1, the need for flexibility and adapting to change. So for a really long time, the absolute pinnacle of mass production was the transfer line. You'll also hear it called a dedicated manufacturing line. Think of your classic automotive assembly line, where a massive engine block just moves continuously from station to station. And hey, it's incredibly efficient for high-volume identical parts. But here's the fatal flaw. What happens when product designs change? In today's market, demands shift incredibly fast. If you need to tweak a product's shape or switch to a totally different part, rearranging those massive, dedicated machine tools is just brutally costly and time-consuming. Modern manufacturing desperately needs flexible, quick change-out solutions if it wants to survive. Which brings us to Section 2. Enter the machining center, a true paradigm shift. Developed initially back in the late 1950s, this concept represented a massive philosophical shift in engineering. The source text highlights this perfectly with a great quote. In machining centers, it is the machining operation that is brought to the workpiece. Instead of lugging the part over to the machine, the part stays completely stationary. The workpiece sits firmly locked onto a pallet or a module, while all the intricate cutting, drilling, and robotic magic happens entirely around it. It literally upends the traditional factory floor logic. I actually love to frame this as the master chef approach. Picture a world-class chef standing in a highly optimized kitchen. They aren't running to the fridge for every carrot or sprinting across the room for a whisk. Every ingredient, every pan, every single tool is automatically handed to them exactly when they need it. A machining center is basically that, an all-in-one, one-and-done system. Because the workpiece isn't being constantly refixtured, productivity absolutely skyrockets, labor requirements drop, and the chance of misalignment shrinks to near zero. And once a part is finally done, an automatic pallet changer swaps it out for a fresh one in just 10 to 30 seconds. It's wild. Let's look under the hood in Section 3, Anatomy of the Machine, inside the center. To start making sense of this, we really need to understand the physical space the machine operates in. This brings us to a key definition, the work envelope. Now, this term was actually originally borrowed from the field of industrial robotics. It refers to the maximum dimensions that the cutting tools can reach around a workpiece inside the machining center. Basically, everything the machine needs to do to shape the metal has to fit within this highly controlled, three-dimensional spatial envelope. Now, what's really interesting here is the mechanical wizardry of the swing-around automatic tool changer, or ATC. Remember our master chef analogy? Well, this is the robotic sous chef handing over the knives. Depending on the exact design, a machining center can store anywhere from 40 up to 200 cutting tools in a magazine or chain. When a new operation is needed, this swing-around arm automatically grabs a specific tool holder, usually identified by barcodes or specific coded tags, and seamlessly transfers it right into the machine spindle. No human intervention needed. But the anatomy isn't just mechanical. It's highly sensory too. Modern centers use what are called touch probes. These are multifunctional tools inserted right into the spindle to physically contact the workpiece. They determine exact reference surfaces, feed data directly back to the machine's control system to select proper tool settings, and they even automatically compensate if a tool has worn down slightly. They can also perform online in-process inspection of the parts being machined. They ensure absolute perfect accuracy without a human ever having to take a single manual measurement. Moving on to Section 4, types of centers, specifically vertical versus horizontal. So the two basic types you're going to encounter are vertical spindle and horizontal spindle machining centers. Vertical machining centers, or VMCs, direct their cutting thrust forces straight downward. This creates a ton of stiffness, making them absolutely perfect for producing parts with deep cavities, like complex molds and dies. On the flip side, horizontal machining centers, or HMCs, are the go-to for large, tall workpieces. The horizontal orientation is awesome because it allows gravity to help clear away the metal chips, and the part itself sits on a pallet that can be swiveled and rotated. This means you can attack the workpiece from almost any angle. And, of course, we certainly cannot forget another key category, the CNC mill turn center. Basically, imagine a computer-controlled lathe on steroids, built with dual spindles and turrets. The real magic here is that those turrets are actually powered. That means they hold actively spinning tools, which allows the machine to perform intricate drilling or milling operations on a cylindrical part, all without ever having to unclamp it, move it to a different machine, and refixture. All right, let's bring it all home with Section 5, Capabilities and Economics, the bottom line. So the crucial point here comes down to scale and speed. Just think about this number for a second, 110 kilograms. That is nearly 240 pounds. That's the maximum weight of some of the massive cutting tools that these automated arms can swing around and change out, and they can do it in up to 30 seconds. Meanwhile, smaller tools, they can be hot swapped in under a single second. The physical capability and sheer strength of these machines are just staggering. And then there's the incredible speed. While standard machines usually run between 4,000 and 8,000 RPM, modern spindles in these machining centers can accelerate from 0 to 20,000 RPM in just 1.5 seconds. And for special ultra-precision applications utilizing very small diameter cutters, they can hit an incredible maximum of 75,000 revolutions per minute. There's almost no way to wrap your head around that. When you're carving solid metal at those speeds, you generate a massive amount of chips, which the machine automatically manages and clears out with spiral conveyors. But look, all this speed, flexibility, and raw power does not come cheap. A top-of-the-line machining center can cost upwards of $2 million. That is a massive capital expenditure. And because of this high initial investment, factories don't just run these machines from 9 to 5. To be truly cost-effective for a business, these centers are designed to run constantly. They often operate across multiple shifts a day, just churning out parts continuously while the rest of the world is fast asleep. So when management actually looks at purchasing a machining center, they have to analyze 4 main economic selection factors. First, the product type, size, and complexity. Second, the specific machining operations and the number of cutting tools required. Third, the dimensional accuracy needed. And we're talking about tolerances as tight as plus or minus 0.0025 millimeters. And fourth, the required production rate. When a factory needs to achieve mass customization, basically producing a wide variety of perfectly precise parts quickly without constant retooling downtime, this huge initial investment becomes absolutely essential. Which brings us to the end of our explainer. I want you to just look around you right now. How many everyday items, from the components deep inside your car to the casing of your smartphone, were shaped by this invisible, high-speed robotic ballet? Once you grasp the sheer engineering genius of a modern machining center, you start to see the entire world of manufacturing in a completely different light. Thank you so much for joining me, and keep exploring.